Hello and welcome to PSIRDEMATICA. In this video, we'll be looking at some basic MPI functions in C. Now, in the previous video, we spoke about message passing and then how to communicate within processes. And in this video, we would look at some basic functions that we can use to do this basic communication within each process. So without wasting much time, let's get started. I'm Joseph Sedem, a tutor at PSIRDEMATICA. We are glad you are learning high performance computing with us. Now, the assumptions still hold, right? We assume that one core can perform just a process at a time, and by so doing, we can use the word process and processor interchangeably, right? Okay. Now, before we talk about the basic functions, let's look at a generic MPI program. So every MPI program basically has these properties. First, we include a certain MPI header, right? And then after including this header, we perform some basic variable declarations, and then we initialize the MPI environment that will call or include all the functions or gets ready to make use of the MPI codes or MPI function calls or routines, right? And after that, we perform some computation and then use some MPI communication calls, send, receive, and other things. When we are done with the parallel side, then we do what? We close the communication and continue with our code, right? So basically, that's how a generic MPI code is, like, or a parallel code is, right? Okay. So the first one is to include the MPI header file. So in C, we use the include MPI.h, right? So we include it aside the including standard input output and all the other libraries or all the other header files that we include. We add this header file as well. And then after that, inside the int main function, right? This accepts some arguments. We will be seeing those arguments shortly. And then while inside this, we perform some variable declarations. After performing some variable declarations, we also decide to initialize, that starts the parallel environment or begin the MPI environment, right? So once we initialize by using the MPI underscore init, you see that the I here is capital I and then the rest is small letters. And then we bring our parentheses, and then this also receives some arguments. These arguments will depend on the arguments that we pass in the int main function. So if this happens, then this starts, or this tells the program that what, from here downwards, we are going to put some parallel codes here, right? And then use the elements or the functions or the things inside the MPI header file. Use them here. Whenever you see them, use them here to perform the parallel computation for me. When you are done and you think you are done with your parallel code, then we use the MPI finalize, right? So the MPI finalize would do what? Close the MPI communications. So we'll wrap up. We'll do some housekeeping and some other things to prevent our program from misbehaving from here downward. You should know that this should not necessarily begin your code, right? This should only begin or come at the portion of your code where you are trying to parallelize, right? Last video we talked about parallel regions. So the parallel region, the parts you think you can parallelize, this is where you start. Those sections, you first start with the MPI init and then you end with the MPI finalize. Always in all your MPI codes, these two should start and begin respectively. So here we look at the arguments that could go into the int main, right? This is the int argc. So the argc just basically talks about the number of arguments that you pass through after running your code, and then the character, this is a character pointer that takes or that keeps a track of the arguments that you add, right, after running your code. So if you include like 4 arguments after running your code, then the int argc will take 4. Okay, it will take 5 because the first argument would be the file name that you are running, and then the rest 4. So that will be 5 arguments, and then the argv will just be the number, the arguments that you add. We'll see that in the next video. Okay, so after performing the arguments, including the arguments, then you do some variable declarations, and then after that we also do what? Start or initialize the MPI environment. And see, here we declared the arguments, and here we put the address of the argument. The address of the argument. If you don't need these arguments, or if you don't need this argument, then you don't have to bring them. In the next slide, we will see what we should bring. And then we put our parallel codes here, and then when we are done with the parallel region, we finalize. After finalizing, you can continue typing, doing your normal serial code or your normal programs. And then when you get to a different region where you want to parallelize, you do the init, you finalize. You keep doing that until you are done with your entire code. So here we realize that we don't want to pass any argument, so we use the null, right? Null means that there are no arguments, or we don't want any arguments. So basically that's what happens if you are not using any arguments. Okay, now you see that from here also we also try to finalize when we are done, right? When we are done. Okay, so talking about the communication, so we spoke about the beginning and the end. So now what goes into the parallel region, right? So first we use the constant, the MPI com world, right? Now this represents a predefined communicator consisting of all the processes. So if we are looking at these in our current or the recent times, this could be like a group, a WhatsApp group, any group that you have, right, that consists of what? The processes that you want to communicate with, the processes that are engaging in the communication, the number of processes. If there are 20 processes, then this communicator or this com world will include those processes with their properties and some other things that you can use with those processes, or you can do with those processes. So we have the com world here, and then we also have the MPI com rank, so the communication rank. So basically this is used to find out which process you are. So any processor that is running this would store or would identify itself by the rank, right? So basically it's more or less like the name. So I am process maybe 1, process 2, process 3, and bear in mind that the ranks of the processes starts from 0 and then continues. So 0 1 0 1 2 3 4 continuously. Now the next function will be the MPI com size. So the communication size, basically this is used to find out the number of processes or the processes involved in the communication, right? The total number of processes that you want to run your code with, or that you want them to perform the parallelization or the parallel code that you have. So the com size will tell you about the total number of processes that you have. Now it will interest you to note that if you pay attention, you see that the constants or the data types, the MPI data types are all in caps, right? Bear in mind that this is C, right? So you see that we have MPI com world, it's all in caps. So this tells you that this is a constant, or this is an MPI data type, right? And this particular one is just a communicator. Then we have MPI. You see that the MPI here is caps, is in capital letters, and then you see that the beginning here is caps, the rest is small letters, right? The rest going is small. So which means that this is a function or a routine if it were Fortran, or and I will call them routines, but here in C this is an MPI function, right? And this function does what? Returns the rank of the processor that is currently running it. So it's what the processor would use to say that, oh, I am this is my name. Basically that's that. And then the MPI com size, you said this is also a function. Why? Because it starts with MPI in caps, the com becomes capital C, and the rest in small letters. Returns the what? The total number of processes that are involved in a communication. Okay, so looking at a demonstration, we see that here we can establish the communicator by using MPI com word. This is a constant, but then we could also use this data type, right? So this is a type, an MPI type. It also returns the communicator, right? But this helps us to assign our own variable name for the communication. So if you think that writing MPI com word, this is cumbersome or this is too much of a work, then you can declare this variable, this any variable name you want, and then you declare the type. The type will be an MPI com communication type. That's the MPI com. This will make this look like this or behave like this. So this will be your own user-defined communicator, right? So here we said we call the function that we supply the communicator that we want, the delivery service that we want, right? The communicator, the institution available. So in the previous video, this will be like our flip delivery, right? But then this is our communicator, and then this is what? The rank. So bear in mind that this is an address, right? Which means that we have to declare a rank variable beforehand, and then we direct or we introduce the address of the rank variable here, so that this rank function will just take the rank of the processor that is running this particular line of code and return it and store it here, and then we can use it in our code. The same thing happens here. So you see that here we are using our declared variable name, right? MPI com, the normal user declared or user defined variable name here, and we still store it. The same goes for the size. So we use our communicator and then the address of what? The user defined variable size variable. And then you could also use this one. That's the user defined what? Communicator, right? And then you run the same code. So basically that's that. Now let's talk about the compilation. So how do we compile this code, right? A parallel code. So to compile the parallel code, you use the MPICC and then the file, right? So this is using what? A relative path, right? So // saying that it's in this current folder. Yours could be in a different folder. You just have to direct the compiler to where the file is, right? You direct it to where the file is, and then if you want to save the output to a different name instead of the a.out, then you can use this option, right? And then wherever you want to put it, so the // will put it exactly where you are in the terminal, right? But then if you want to put it with this file, then you can direct it to the file path here and then give the executable name that you want to use, right? So basically that's for the compilation. Note that the compilation is dependent on what? It's dependent on the implementations that you have. Bear in mind that we have different types of MPI implementation, so we can deal with the compilation in different ways. I use MPI CH, and if you use this, you'll be fine. You will not have any other problem. Okay. Now, the next one we'll look at is running, right? So after compiling, we have to run our code, right? So basically, if you have a single instruction, multiple data code that you want to run, what happens is that we just use the MPI run command and then this is a local option, so you assign the option. This option stands for the number of processes or the number of processes that you want to involve in the communication, or you want to use to run, you want to establish, you want to use to run this particular file, right? So the number of processes, this x is the integer, so the number. So if you want 2 processes, if you want 3 processes, if you want 4 processes, you can engage these 4 processes to run this file for you. Also, bear in mind that this is a relative file path. So if your program is not at, if your terminal is not open in where the file is, then you would have to use your own path to the file that you want to execute. And then, sorry, this shouldn't be .c. This c should live here. It shouldn't be part of this. So the executable that you have from the compilation. A more general one would receive what? Some global options here, and then your local option, and then the file name. Now after the file name, looking at the arguments, then you can pass any argument at all you want, right? You can pass any argument at all you want here, but since we are focusing on the basic functions, we will not talk about any argument. So if you input 5 arguments, then the argc will be 6, because the file name is already 1 argument, and then these other arguments will follow. If you have 2 arguments, if you add 2 arguments, then the argc will be what? 3, and then the argv will contain this file name, will contain this other argument's name, and this other argument. So basically that's for single instruction multiple data. Now in a situation of multiple instruction multiple data, what happens is that here the same thing, the number of processes you need, right, for let's say 1 computer, or for this particular instruction, the number of processes you need to run this particular instruction is x. So if you want 4 processes to run this particular instruction, you use what? 4 here. Then when you are done with this particular instruction, then you bring the colon, right, and then you do what? A new number of processes, right? So let's say this will be 6 for this particular set of instructions. Bear in mind that the processes that are available will run this file, and then the ones you have here will also run this file. Keep that in mind. And we use this for multiple instruction multiple data. Also, there's a more general form where you have your global options and then your arguments after. So your arguments will be here, so, and then your arguments will be here, and then your global options that will be applied to the general cluster. But you don't have to worry yourself if you just be running this code on your machines here, right? So basically that's how we run parallel codes for multiple instruction multiple data. So okay, so talking about what happens when we run the parallel code. So when we run the parallel code, right, so let's say we have our parallel code and we include, let's say, number of processes, right, to be 4. What happens is that 4 instances of this code are created, right? And then bear in mind that as MPI is used for distributed memory, due to be created and then be distributed to the memory of the processes or the processes that are involved, right? But then if you are using them in a shared memory, then to be included in the memory for 4 processes, the potential 4 processes, right? So 4 instances will be created, and each having the same code. They have the same code, right? And then they all run. When you do the MPI run, each processor runs this thing. Bear in mind that we are assuming that a processor runs a process at a time, right? So each processor performs or runs this process at the same time, right? So it will run it when it gets to a position or a place where it is specifically assigned to, let's say, processor 0. The processor 0 will run that code. If it gets to a place where you have processor 1 to do that, Then processor 1 will run that region. Processor 2 will also run its region. Processor 3 will also run its region. So basically, note that the same instance of code is created in memory with respect to the number of processes that are involved. Then this is where the distribution comes in. If you have a machine like interconnected computers, then these copies will be distributed to the memory of each processor that would run this program. If it is a shared memory, then that space is allocated, right, for the process for this to happen. First, they share the space where these 4 instances are created. Then if in a code you are supposed to store a particular data in a portion, and that data takes 2 gig, then 2 gig each is allocated in memory. Keep that in mind. So basically, that's what happens when you run a parallel code. In the next video, we would look at how to code or create a simple hello world parallel program. If you like this video, don't forget to like and subscribe, and put your comments in the comment section below, and then we'll see you in the next video. Thank you.